Okay, so in this lecture we will look at a generalization of the Parseval's theorem for Fourier integrals. So we saw how, if you are able to write a function as a Fourier series, then the average of the square of the function, right, is related to the sum of the squares of all these coefficients. Or if you are writing it in the exponential series, then it's the sum of the square of the moduli of the coefficients, right? So there is an extension of this theorem which is applicable also for Fourier transforms, and that's going to be the content of this lecture. And once again, just like with Parseval's theorem with Fourier series, these two has some very nice applications which follow from Parseval's theorem, right? So that's what's coming up in this lecture. Okay, so in order to write down Parseval's theorem for Fourier integrals, first we will work out a generalized version of Parseval's theorem involving Fourier series for a periodic function itself, right? So we saw how the product of a function with itself, and if you averaged over this quantity, was given in terms of the coefficient. So in fact, what you could do is consider two periodic functions, f of x and g of x, expand each of them, which are both periodic with the same period, let's say to pi in this case, and f of x can be expanded in a Fourier series, g of x is expanded in another Fourier series. So you have all these coefficients an and bn for the first function, and an prime and bn prime for the second function. So then, instead of considering the average of f of x squared or the average of g of x squared, you can also consider the average of f of x times g of x. So if you do this, right, so you can show that in fact this average value 1 over 2 pi integral minus pi to pi f of x g of x dx is given by 1 over 4 a naught prime, right? So only the diagonal terms, so to speak, will remain, right? So an will go with n prime, and then you get this customary factor of half, and likewise bn will go with bn prime of an overall factor of half outside, and there's a summation involved over all n, both for these an terms and for the bn terms, right? It's not hard to show this result, right? And I urge you to convince yourself that this works out. So the key idea is, of course, that these functions are orthogonal to each other, right? So they are members of this basis, which is an orthogonal basis. We have seen this, and so if you take any cosine nx and multiply it with some other cosine of mx, as long as n and m are not the same, the average value of this product is going to go to 0. But on the other hand, if n and m are the same, then you get just 1 in the well, you get a half, right? So it's the average value of cos squared in a period, so you get a half. So these are orthogonal but not normalized. So it's simply because it's straightforward to work out this integral of any of these basis elements with itself. The inner product of any element with itself is straightforward to work out. And likewise also with sine squared of nx, you're going to get half, but sine nx times sine mx, the average value is 0, right? So this is an immediate consequence of the same result we used to prove Parseval's theorem, involving just a single function. Now it turns out that this result in fact generalizes to Fourier integrals, right? So let's say you have f1 of x and f2 of x are two functions, non-periodic functions, and you find their Fourier transforms, and let's say they are g1 of alpha and g2 of alpha. So we have g1 of alpha is 1 over 2 pi integral minus infinity to plus infinity f1 of x e to the minus I alpha x dx, and likewise you have another expression for g2 of alpha, right? So if you take the complex conjugate of the first of the above equations, right, so the generalization of this result for Fourier series, one has to be a little more careful and has to work with complex conjugates of one of these functions, right? So like we discussed when we were doing linear algebra, if you have a real field, then in the inner product of these kinds of vectors, you can just think of them as the integral minus pi to pi f of x g of x dx, for example. But if you allow for these functions to be complex, then the bra vector is going to have to there is a complex conjugation associated with going to the bra vector. So the inner product is going to be not just f of x times g of x, in terms of alpha. So you will have to make one of these, you have to take the complex conjugate of one of these functions, right? So f1 star of x and f2 of x will come in, and g1 star of alpha and g2 of alpha will come in, as we will work out in detail. So let's say you start with these definitions. You have g1 of alpha and g2 of alpha. Now you take the complex conjugate of the first of these equations. So you have g1 star of alpha is equal to 1 over 2 pi minus infinity to plus infinity f1 star of x, and then you have e to the I alpha x instead of e to the minus I alpha x dx. Of course, nothing changes. Now we multiply this g1 star of alpha with g2 of alpha and then integrate from minus infinity to plus infinity. So g1 star of alpha, we already have this expression for g1 star of alpha. So we plug this in, and then g2 of alpha remains as it is, d alpha as it is, integral of course minus infinity to plus infinity. So then we see that 1 over 2 pi, this f1 star of x, comes out. So dx also comes out. So you have dx f1 star of x integral minus infinity to plus infinity e to the I alpha x g2 of alpha d alpha. So I have just rearranged these various factors, right? So this part doesn't care about this integral involving alpha. So I am allowed to bring this stuff outside. And then now I observe that in fact this integral is nothing but the inverse Fourier transform of g2 of alpha. But the inverse Fourier transform of g2 of alpha is just f2 of x. So this is equal to 1 over 2 pi integral minus infinity to plus infinity dx f1 star of x f2 of x. So what we have managed to show is really an extension of the result for the Fourier series, right, involving two functions which were periodic. But now if you have two functions f1 and f2 which are not periodic, so if you do this integral minus infinity to plus infinity dx f1 star of x times f2 of x, and then put in this factor 1 over 2 pi, this is going to be the same as the integral minus infinity to plus infinity g1 star of alpha g2 of alpha d alpha. So now if you say that these two functions are the same, let's say f1 and f2 are the same and they're both equal to f, then of course the Fourier transforms also are going to be the same, g1 equal to g2 equal to g. Then we have integral minus infinity to plus infinity mod of g of alpha squared d alpha is equal to 1 over 2 pi integral minus infinity to plus infinity mod of f of x squared dx, so which is basically the Parseval's theorem. So this is a generalization of Parseval's theorem for Fourier integrals, right? So this factor is of course dependent on the manner in which you have defined your Fourier transform and inverse Fourier transform. But like I said before, you have the freedom to define your Fourier transform, and then automatically it fixes the inverse Fourier transform for you, right? And it doesn't matter how you share this factor between the Fourier and inverse Fourier transform, as long as you're consistent throughout in your calculation. Okay, so let's look at an example where we apply this this idea, and so we're going to work out the Fourier transform of the Gaussian function, right? So I have f of x is equal to exponential of e to the exponential of minus x squared by 2 sigma squared, right? So well, I mean, you have to read this carefully and understand that really I'm referring to exponential of minus x squared by 2 sigma squared. So if I do this, maybe it will look better. Yeah, I guess this is a bit better. But so the key point is that, so this is what I am referring to. It's an exponential over all of this stuff, and likewise, so this is going to appear later on as well. So if I want to find the Fourier transform of this function, so this is the Gaussian function, right? So you have seen what it looks like. It's peaked at the origin, and then it tapers off and it falls off, you know, very quickly on both sides, and it's symmetric about the origin. So if you take the Fourier transform of this Gaussian function, you have 1 over 2 pi integral minus infinity to plus infinity this function times e to the minus I alpha x dx. And so the way to proceed to evaluate this integral is to do what is called the completion of squares. So you have an exponential of minus x squared plus 2i sigma squared alpha x divided by 2 alpha squared. So this you can rewrite this as x plus I sigma sigma squared alpha the whole squared, and then you have an extra constant part which has to be subtracted out. And so if you take if you carry out this exercise carefully, so you will get an extra factor 1 over 2 pi is already there. Then you have an exponential of minus alpha squared sigma squared by 2, and then you have this integral which is actually just a standard Gaussian integral, except that x seems to be shifted by some constant complex number, right? So you can make a change of variable x to x plus sigma squared I alpha, right? And then it's just this standard Gaussian integral, right? So one has to be a bit more careful and to be completely correct and use the subtleties of complex variables. However, so here we will just assume that it's all good, and indeed it is true. So complex variables are involved, so then you have to be a bit more careful. But so if we'll assume that it's all good, and so indeed g of alpha is equal to sigma over square root of 2 pi e to the minus alpha squared sigma squared by 2, right? So this part will just give you 1 over square root of 2 pi sigma, and right, so this part is going to give you a square root of 2 pi sigma, and so sigma remains, and then one of these square roots of 2 pi will cancel, and then you're just left with sigma over square root of 2 pi times e to the minus alpha squared sigma squared by 2. Now if we invoke, so we have managed to find the Fourier transform. If we invoke Parseval's theorem, right, so into this relation, so we immediately see that you get minus infinity to plus infinity sigma squared over 2 pi e to the minus alpha squared sigma squared d alpha, right? So this is integral of g of alpha mod of this squared, and then you have to put in this factor 1 over 2 pi, and that's followed by this integral minus infinity to plus infinity f of x the whole squared. So that's going to become e to the minus x squared by sigma squared dx, right? So which is evidently true because you just recast this in this form, right? Instead of 1 over 2 pi, you write it as 1 over square root of 2 pi on both sides, and then you bring in one of these factors sigma to the other side. So you have 1 over square root of 2 pi sigma here on the right hand side, and on the left hand side you rewrite this as 1 over square root of 2 pi 1 over sigma, then exponential of minus alpha squared divided by 1 over sigma squared d alpha, and then you see that both these integrals are really the same, the left hand side and the right hand side, and they're both equal to 1, right? So they're both the standard Gaussian integral, and so in fact we get a result which is not a surprise, right? So in quantum mechanics you might have encountered Fourier transforms of this kind. Gaussian integral particularly is of very great importance. So there the physical interpretation is it has to do with wave function conservation, right? So it doesn't matter in which basis you expand your wave function, right? So if you sum over all the probabilities of it being in all possible eigenvalues corresponding to that operator, then it has to add up to 1, right? So that's one way of thinking about this if you're looking at it from the point of view of quantum mechanics. But the result that the Fourier transform of a Gaussian is a Gaussian, and therefore the inverse Fourier transform of a Gaussian is also a Gaussian, right, is of great importance, and it appears in all kinds of contexts including quantum mechanics. So that's all for this lecture. Thank you.